So this is mainly a performance talk, and I hope everyone's interested in performance here. So I'm going to talk about some of the pitfalls you run into when you try to parallelize the random forest algorithm. And I'll give an introduction to the problem and talk about random forests. I'll speak specifically about an implementation that I've done. I'll give some examples and some anecdotes and discuss ongoing work, then provide a brief summary and talk about future projects. So this talk is actually about a project called the Arborist, which began as a proprietary implementation of the random forest algorithm. And the aim at the time was to provide enhanced performance across a wide variety of hardware, data, and workflows. And at the time, and we're talking maybe 3 years ago now, GPU acceleration was a major concern. I mean, the whole reason the effort started was a hedge fund manager approached us and asked us to parallelize the application for the GPU. But the venture under which this was done has folded, so the course was subsequently open sourced and rewritten. The project name is Arborist with an A. The Pi package will be called Pyborist, and Arborist with an R is the R package. The project design goals are a language-agnostic implementation relying on a compiled core. We're looking for minimal reliance on callbacks and external libraries. And a key goal is to minimize data movement. I claim that's where you get most of your speed up. And I'll go into what data movement is in case anyone's not up on that kind of thing. We also strove for ready extensibility of the code and a common source base for all subsequent spins. So to sort of recap what the random forest algorithm is, it's a decision tree method, a binary decision tree method. It's a prediction method that presents a series of true-false questions about the data. And the answer to a given question determines which of two questions to pose next. And so it's a successive true-false branching relationship that justifies the term tree. Now note that different data will take different paths through the tree. Where you end up during your traversal is referred to as a terminal node or a leaf, and that's how you get the score for the data that you're trying to evaluate. And you can build a single tree and refine it with subsequent steps, and that's what boosting is all about. But I'm here talking about forest approaches in which you grow typically hundreds or perhaps 1,000 trees. And the overall score that you report in the case of regression is an average, and in the case of classification, it's a plurality. Now, it's actually a trademark term, but so I'm very careful to say random forest algorithm, but I don't think that many people make the distinction anymore. So what it's trying to do is predict a vector of data. The term of art for that is the response. And if the data is numerical, it's termed regression. If it's categorical, it's termed classification. And it trains on a design matrix of observations. Column-wise, they're referred to as predictors. And the predictors can either be numerical or they can be categorical, known as factors. Each individual tree is trained on a randomly selected or bagged set of matrix rows. I mean, that's kind of what distinguishes a tree at the beginning of training. And predictors are randomly sampled throughout the training operation in a way that's separately or independently done for each node that you're trying to train. Validation is done on the held-out subset, which is, of course, different for each tree. And this enables you to do an independent prediction on separately provided test sets. Excuse me a minute.
Are there slides that go along with this?
Oh, thank you. I knew I was going to forget something. You picked the right time. Okay. I wondered what I was going to screw up, and hopefully that's the only thing. So if we're looking at training as a process of tree building, we begin with a root node that's conceptually coupled with the bagged data set. And one way to look at bagging, in which I emphasize during this talk, is to think of it as an indicator set of row indices with multiplicity. So if you're doing sampling without replacement, or I'm sorry, with replacement, you're going to sample some rows many times and some rows 0 times, and that's why I'm talking about an indicator set here. And subnode construction or splitting is driven by information content. Nodes with sufficient content will branch into 2 new subnodes. And as part of this process, the branch itself is annotated with the splitting criterion, which determines its sense. In other words, whether you branch left or right. And again, if there's no splitting, the node is terminal. It's a leaf. And you can perform this, this training operation however you like. You can do depth first, breadth first, a hybrid approach. It's really up to the implementer and the various reasons for doing these various ways. Construction terminates when the frontier nodes, that is the current collection of leaves, simply exhaust information content. But the user can also specify a termination criterion, and there are several of those commonly in use. So now, to think of building trees as conditioning, which I think is key to accelerating the algorithm, splitting has the consequence of partitioning the training data into progressively smaller subsets. So in a sense, what you do when you test is also what you do when you train. You're conditioning the data into smaller and smaller sets. The left successor to a node that's split inherits the subspace satisfying the criterion, and the right successor nodes inherit the complements. So from this perspective, the root node trains on all bagged observations, and successor nodes train on data that's conditioned by the parent. And as we'll see, and I think this is an important distinction, the conditioned subspaces can be characterized as row sections of the design matrix. So in other words, if you look at it that way, the splitting criteria defines successive bipartitions on row indices. And if you look at it from that perspective, you can easily see that the algorithm's got to terminate naturally. So the splitting criteria are formulated as either order or subset relations with respect to the predictor on which you're splitting. So for example, if it's numerical, let's say P, if the cut is less than or equal to 3.2, let's say we branch left, otherwise branch right. A typical style of criterion for a factor predictor will be a subset membership relationship, again, branching left or right. But at a given node, the candidate criteria are obtained over randomly sampled sets of predictors. So that random sample is going to differ for every node that you train. But within a predictor, the way you come up with a criterion, a candidate criterion, is to evaluate series of left and right trial subsets. For the numerical predictors, those are simply distinct cuts in the linear order. So if there are n indices, there are n-1 cuts. For factors, what you're doing is grouping by runs of identical value, and trying to partition those into 2 subsets. So you've got a factorial relationship going on, or an exponential relationship. The overall criterion is derived from maximizing what's known in the trade as an impurity. And the idea is that you're somehow trying to find a break in the predictor that best separates the response into 2 sets. But when you get into the bowels of this algorithm, you'll note that the trial scoring is a function only of response, evaluated according to predictor order. It's irrespective of predictor, but the node is scored according to a unique set of response indices. So the only thing that the predictor is doing is dictating the order that you're walking those indices in. The values play no roles. So we're only really ever interested in predictor ranks and runs, at least when we're training. I mean, when we're scoring, it's a little different story. So each trial, in particular the winner, determines a bipartition of predictor ranks. And because of this pseudo-bijection in the title of this slide, you can see that induces a bipartition on row indices. One set of row indices characterize the left branch, and one set characterizes the right branch. And I claim that that's the key to accelerating this algorithm. So throughout training, you can look at the frontier nodes as representing a highly disconnected partition of the original bagged data as row sections. And this little table sort of gives you an idea of how bad things can get when the algorithm is actually training. You're looking across by row, so you're either doing one of regression or a classification. The information criterion is weighted variance in the case of regression. For numerical predictors doing regression, there's very little work. It's a It's just an index walk accumulating local maxima. But when you go to factor prediction, first you've got to accumulate the runs, and you've got to sort them, then you've got to walk the set, thankfully in linear order. With classification, again, the numerical predictors are fairly cleanly dealt with. But when the predictors are factor, things can get pretty ugly. Not only do we have to build the run sets, but we need to walk the power set of those runs. Typically, if you've got more than 10 runs, rather than do thousands of iterations, you just resort to sampling. That's often what's done. There is a shortcut you can take in the case of binary classification. And just as an aside, just as in linear algebra, the appropriate treatment that in training, if you want a fast implementation, depends on your data. Think of singular value decomposition. You pay particular attention to the symmetry properties of your data in choosing how to decompose it. You're not interested in symmetry necessarily here, but you do have other things that you're concerned with. If you know you're just doing regression with numerical predictors, you have regular access patterns, and it tends to run quickly. If you've got constraints in the values, you may be interested in using a smaller data type, doing some kind of numerical simplification. If you've got a lot of ties, you may be interested in a sparse representation. So a custom implementation is going to rely heavily on the answers to such questions. And therefore, if you're trying to do an implementation that's extensible, you want to make it easy to customize. I'll speak briefly about data locality, which is kind of the central problem we're trying to solve. Recall that computers store data in a hierarchy. The CPU operates on registers, but once something can't fit in a register, it falls back into a hierarchy of caches. Beyond that, there's random access memory, and beyond that, there may be a hierarchy of disks holding the data. But where you want them is in the register. And getting the data into the register consumes a lot of clock cycles, the higher up you are in this hierarchy. So performance is best when you're close to registers. And by a similar argument, when you're looping over vectors, the most efficient way to do it is when consecutive iterations are spaced by a predictable amount and relatively short strides. And that's the regular access pattern that allows the compiler and the hardware to do a good job. And if you are at all interested in the GPU implementation, you've got this problem in spades, because GPUs tend to specialize or excel at very highly regular data access patterns. A few observations about the algorithm. You may have picked up on the idea that splitting is an embarrassingly parallel process. The trials can be evaluated on all the nodes in the frontier independently at the same time. However, you do need some mechanism for keeping track of the ranks that correspond to the node indices. These vary with the predictor. A naive solution would be simply, when you're trying to split a node, to sort the predictors. That's really slow. That's what some of the older implementations do, and they do not scale well. So, I think the first thing people notice when they're trying to speed up this algorithm is to do a pre-ordering. Well, with pre-ordering, you can do an index walk and accumulate per node state by just looking up what row index you're currently at. And that's the original approach that the Arborist employed. But that has little or no data locality because the index lookup is irregular. And it requires a large state budget because you're swapping a lot of these partial sums in and out every time you change the node that you're currently operating on. So we came up with this idea of restaging. And that's simply to maintain a separately sorted set of state vectors for each predictor according to node. So you begin with this pre-ordered list or set of vectors, and you update it at each level of the tree via what's known in engineering circles anyway as a stable bipartition. That's the current approach we use. Data locality improves with tree depth because we're moving things over shorter and shorter distances the further down the tree we go. There's only a modest amount of state to move if you're using double precision values. With the other state, it amounts to about 16 bytes, which you're going to get several in a single cache line if you do it this way. And this has the consequence that splitting is now quite regular. You're able to fetch the next datum or prefetch it for the next iteration of the loop. And a surprise that we noticed in working on a GPU implementation is actually the restaging itself can be done in parallel on SIMD hardware. The SIMD hardware is what most GPUs are built with, but you're also seeing SIMD engines on the newer Intel chips and ARM chips. So, these things are ubiquitous. And the scheme you use there is known as a parallel scan, which, if you're a parallel programmer, you probably are very familiar with that. Excuse me a minute. So the code is organized as C++ compiled code with various language front ends. R was sort of the impetus in the early development, and Python is now under perhaps active specification is a more accurate term. We're using front-end bridges wherever possible. R has a glue language, a template glue language called RCPP, and I intend to use Python for this project, and I'll go into some of the reasons for that. Again, we want to minimize the use of front-end callbacks. Currently, what we have to have some front-end or external library provide are random number generators, a sampling algorithm, and sorting. But one nice thing about the project and the way it's organized is that the common code base is used to derive all versions. And so far, I've been able to achieve GPU functionality just by subtyping. The look and feel is guided by existing packages. We're not really trying to do anything new or whiz-bang other than make it go fast. Many options are the same, but we support only numeric and factor data. If you've got a deeper data type, a more sophisticated data type, you've got to derive the factors and numerical data underlying. And the reason for that is to try to get away from Python-specific, R-specific, Julia-specific data. One distinguishing feature that we have is we're using Bernoulli sampling instead of sampling without replacement to choose among our predictor sets when we split a node. And in an example that's coming up, I may illustrate why that's not necessarily a good idea, and I may change that. The implementation is breadth first, and it allows us to introduce a specification of the terminating level. We also introduce an information-based stopping criterion called min ratio, and that's about as close as we get to regularization here. I'd like to do more with regularization. I don't know that this theory is well flushed out. This is what we're offering currently. We do not limit factor cardinality beyond the size of a bucket that an integer fits in, but if you're a practitioner, you know that's a blessing as well as a curse. And anyone who's familiar with these packages know that there's plenty of stuff we haven't implemented yet. The distinguishing features of the code is this decoupling of splitting from row lookup, restaging and a highly regular node walk already mentioned. And both stages benefit from the resulting data locality and regularity. Restaging is maintained as a stable partition. And we produce a lightweight serialized pre-tree, and that's allowing us to go from a multi-node implementation. We can ship data across very cheaply because I claim it's minimal. I mean, about the only other thing I can think of to do with it is to compress it, and perhaps that's an option further down the road. We support a rich intermediate state, and in fact, our state is rich enough that we can derive quantiles natively. You don't have to call anything else. All you have to do is specify that you want quantile regression, and you've got it. It's also set up to allow workflow internalization in sort of what the user might call loopless behavior. The only example of this at the moment is nonparametric resampling, but if people can think of other ideas, we're more than willing to entertain implementing them. So early experience, again, we began with an R front end, and we compared performance with the well-known random forest package in R. We worked with medium data, by which I mean things that could fit in memory. And we typically noticed speed-ups at about 500 to 1,000 rows. We observed linear scaling with the number of predictors and the number of trees as expected, and log linear scaling with the number of rows. And also as expected, regression is much easier to accelerate than classification. Here's just a short example that it's German credit scoring data. It's got 20 predictors. It's very small, 1,000 rows. And all I'm trying to illustrate here are some general speedups over the random forest implementation in R. as well as the relative merits of this Bernoulli sampling versus the without replacement sampling that random forest uses. So the Bernoulli sampling is in blue, and the without replacement sampling is in green. And the y-axis is misprediction rate. So I'd say qualitatively they're about the same, but I'm a little bothered about the behavior to the right. We're doing this Bernoulli sampling, and we seem to be consistently going above what the R implementation is capable of. Now, this is just one data set. I mean, it's got to be explored in more detail. But because of the high variance of Bernoulli sampling, I'm seriously considering offering this without replacement scheme, at least for low predictor count. And the minimum is more or less where it should be, somewhere between 4 or 5 samples per node is about where you'd expect to see the minimum. And this is a ratio of execution times. The Arborist is consistently faster, but I'll say that the left really isn't telling you much on this graph because the Arborist isn't really doing much at low probability. It's at the higher probability that it's doing more work, and there it's getting consistently faster over the random forest implementation. And this is another example that appeared in the popular press just a few weeks ago. There was a guy doing benchmarking of various random forest packages, and he specifically excluded the Arborist because he said it was too slow. And he was working on airline flight data, and he was working with that data has 8 predictors, various row counts up to 10 million. It turned out the slowdown he observed had actually been fixed on the GitHub version. He just didn't have access to it and had no way of knowing this. But it was a really great test case, and I wish I had more test cases like that because it caused me to look much more deeply at some of the options we were offering and how we were doing things, and that's the reason I bring it up. For one thing, because we were so heavily biased toward doing things on a GPU, we were parallelizing by predictor. And now, there's no reason just to concentrate on predictors. You can parallelize across all pairs, all splits and all predictors at the same time if you've got the cores. We were also not paying a lot of attention to class weighting, which you really need to do with unbalanced data. That's been dealt with. And for speed up reasons, we introduced this binary classification scheme for high cardinality factors, and that's an n-log-n algorithm. But this points to the need for more and broader testing, and that's one reason I'm here. I mean, I really want to see people beat this thing up. And let me just briefly comment on how we got into some of the early results we saw with GPUs. So we had a pilot project. This is back when this was still a company, with a group at the University of Washington, and they had some HIV patient data. These were individually SNPed. In other words, SNPs are single nucleotide polymorphisms. They're places in the genome that humanity differ by. They're a good way of trying to figure out whether you have a predisposition to certain diseases. And they were trying to determine whether there were such predispositions in HIV patients. And this particular data set had up to 1 million predictors, although I think in the lab they actually had a lot more. So what we did is we spun off bespoke CPU and GPU versions specifically for this data set. Because that's a common criticism when you're comparing GPU and CPU versions. You know, did you do all the things you needed to do for that data? Well, the answer was yes in this case, or we believe it was yes. The GPU version, we got to the point we were training each tree almost entirely on the GPU. About all that was left was a controlling loop run on the CPU. And the following graph just illustrates the potential for this kind of data. As the number of predictors goes up, we rapidly approach a threshold of about a 50-fold speed up if we're using the GPU training. Now, there is a bit of a drop off to the right, but I claim that is a problem with the data frame feature that we used in R. You know, it's a linked list-based feature, and we're trying to read data from it, and it's simply very slow. You can always amortize that by throwing more trees at the problem. But anyway, we seem to be topping out at 50-fold acceleration here. That turned out to be an ad hoc version. It was not scalable as implemented. It's been rewritten since the company folded. But we are now implementing restaging as a stable partition via parallel scan on the GPU. And I approached some engineers at NVIDIA about whether this was the right way to approach restaging. They concurred, and they anticipate good scaling to much larger data sets. But in general, your data sets are not going to look like this. I mean, you could have called that a cherry-picked data set other than the fact that we didn't pick it. In general, if you can recall that table I threw up earlier, when you've got mixed predictor types with multiple cardinalities, you've got huge load balancing challenges. Now, you do have a dynamic parallelism option on the GPU, but you still, because of this predictor selection problem, you're going to be thwarting data locality every step of the way. It's a really tough problem to do the general case on the GPU. I'm not saying you can't do it, it's a lot of work. And I think the lowest hanging fruit for the GPU right now may be these specialized data sets. So, however, you may get good speed up by doing just the regular regression numerical case on the GPU. I haven't tried it yet. But you've still got, because of the row orderings that you need to have when you do restaging versus when you split on the GPU, you've got to do something like a transpose. That's slow, it's doable, but it is one of the problems you're going to face if you try to do a totally GPU-based implementation. So for now, the emphasis is on splitting on the CPU because you've got all these cores you can split over, and restage on the GPU. As you can imagine, to do it that way, you're going to be shipping a lot of data back and forth. You're going to suffer a lot of latency problems. Well, the solution I'm proposing to this is to split one tree on the CPU while you're restaging another tree on the GPU and cover up the latency via a pipeline. And that's what I'm in the process of working on. So a little more about CPU level parallelism. Again, the original work focused on predictor level, but we've emphasized wider data sets where you had a lot of predictors, and you don't always have that. Node level parallelism has emerged as an equal player thanks to this flight delay data. But you know, the specter of false sharing looms its ugly head as you get a high core count and you get fairly closely spaced data. If you're not familiar with false sharing, it's just that multiple threads are trying to write to the same section of the cache. The hardware cannot arbitrate, so it's going to sequentialize the data accesses. There are ways to avoid that in the coding. You just have to be mindful of it. That's all I'm saying is, you know, we've got to pay a lot more attention to that now, particularly as people start trying this code out on Amazon web servers. But the infrastructure is now in place to support a hierarchical parallelization model in which a head node actually does the predictor ordering and then scatters copy to various other nodes. So that way, multiple nodes can each train blocks of trees using their own multi-core hardware and with GPU participation if there's a GPU around. And then the head node gathers all the pre-trees, builds the forest, and does the validation. Getting this ready for prime time is more a matter of scheduling and tuning than anything else. So another couple words about load balancing. Again, mixed factor and numerical predictors offer the greatest challenge, especially for classification. And in some cases, we may benefit from parallelizing the trial generations themselves, where I'm talking about this kind of combinatorial blow-up that you see with factor-based predictors. But irrespective of data type, you've got this inner-level pass that's inherently sequential that you've got to contend with. And again, it may make sense to pipeline to do the inner-level pass from one tree while doing the splitting from another. But again, this is just going to involve a lot more performance testing to investigate. So some additional projects underway. I'm working on a sparse internal representation. It's just starting out. The main challenge is defining the interface with the host languages. It really has very little to do with the internal implementation. Another problem that I'd like to solve sooner rather than later are how you deal with NAs. R has several semantic variations on how to deal with them, and I'm not acquainted with how one typically does this in Python, so there's a learning curve there for me. And finally, there's this whole kind of movement toward post-processing of random tree data that's starting to emerge. There's literature now about feature contribution analysis, and I'm trying to get these trees fashioned in a form that makes it easier for developers of other packages to go and offer these graphical tools to explore feature contributions. So I'll talk briefly about the goals of the Arborist. And that's to encourage flexing and testing by the broader machine learning community. I mean, machine learning people seem to want to use Python, so let's go there. But we'll honor the precedent of scikit-learn in terms of features and style. But I want to provide R-like abstractions such as data frames and factors. I mean, I think, if you want to get work done, you need something like that. But I, at the same time, want to minimize the impact of the host language on user data. It would be really nice if a person could take the same data with minimal processing, or post-processing perhaps, and move it between R and Python as needed. And that's really going to stress the software organization and the design. So the decisions I've made so far are to implement the bridge in Python because of its emphasis on compilation. Panda support will be there because Panda supports data frame and categories. And so far from what I've seen, I'm really impressed with the way Pandas does categories. I believe it's better than ours, and I'm an R person. And using NumPy for random number generation, sorting, and sampling callbacks. And I've considered some other options like Swig, CFFI, and C-types, but I'm becoming sold on Python. But if people have opinions, you can accost me in the hall and tell me what your opinions are. So in summary, we've only adhered to a few rigid design principles, and that's constraining data movement and maintaining a language-agnostic compiled core implementation. We've stuck with a common source base, we still do. There's plenty of room for improvement. I don't claim to have all the answers, maybe just a few. But right now, the emphasis is on load balancing because I believe that's the lowest hanging fruit, both for the CPU and the GPU. Longer term, actually medium term, solicit help and comments from the community, both Python, R, and perhaps Julia, we'll see. I'd like to offer expanded use of templating because it's going to allow users to build their own implementations with the types they need for the job. Everybody always wants out-of-memory support, so that's a direction to head in. And this may be a pipe dream, but perhaps one day it will be possible to sniff the data matrix and see which of many implementations you might want to run on your data set. And something that's very easily done will be to provide plugins for other splitting methods, not just Gini and weighted variance. That's just a matter of putting them in the code. I mean, there's not much to that. And I'd like to internalize additional workflows. So thanks very much to Steve Elston of Quanta Analytics for suggesting that German credit scoring data. Thanks to A.B. Flaxman, whom I'm working with on sparse data representations and the Pi implementation. And a special thank you to Seattle Puppy, which has been a great organ for organizing and sort of getting the word out about Python use in the community at all levels, whether it's just helping people out or doing something really analytics-based like this. And I think we're at 35 minutes, so I think there's time for questions, and that's how to get me. Sir.
So I also come from an R background, so I'm very familiar with the random forest algorithm in R. And one of the things that whenever I have data that's taking forever to run with this algorithm, like I'll go to that mtry variable and I'll say, okay, let's limit the number of variables I'm trying at each partition. I was just wondering, have you seen anything interesting, with, when you go to parallelize that, how does that come into play?
Oh, it's a pain for the GPU because it gives you data locality issues. I mean, unless you just want to always operate on all predictors and just throw away the ones you don't use. But,
What do you mean data locality? Maybe I'm not familiar.
Okay,
Register the...
Yeah, on the GPU, you're talking about what they call local memory. And you've got to pull in as much data to fill local memory as possible, otherwise you're wasting resources. And if you're only looking at a few predictors at a time and they're sparsely spaced, you're just going to be pulling in things you don't need. And I think the correct way to do this on the GPU is to have a secondary staging pass which is knowledgeable about the next level in the tree and packs the data accordingly. I mean, that's all I've been able to come up with so far. But I'm not being paid to do this research, so I mean, it's kind of in my spare time. Sure.
So what do these systems look like that you're running these on today? Do you have, CPU cores and then like multiple GPU slots?
Oh.
Processing, or are we looking at just using the existing GPU that's on the system?
Right now, I'm just working with some development machines that I have locally, and we're talking 4 cores, 1 GPU of a fairly recent vintage, and then once I'm satisfied with that, I can jump up and start using Amazon nodes that have 1 or 2 GPUs attached. But I'm limited by the budget available for this machinery and the amount of interest in the community. So the more interest there is, the bigger the systems that this will be tested on. But I'm starting small. Sir?
The multi-GPU, what about discrete GPU and integrated?
Oh, yeah. That's wide open. And we're seeing more and more internal, you're talking about the on-die GPUs. Yeah, I think there's plenty of potential for those things. I just haven't gotten there. Yeah.
You mentioned exploring different nonparametric resampling techniques.
Oh, just one at the moment. Yeah. Well, internalizing workflows. Yeah.
So my question is going to be, have you seen any key bottlenecks, for example, with bootstrapped aggregation that you want to overcome, or other reasons why you're exploring other types of nonparametric?
Okay. Yeah, I probably misspoke if I said that. What I meant was I'm looking for other workflows to internalize. I view the whole bootstrapping, resampling thing as a done deal. I mean, all I'm doing is permuting the why, the response, the training response, and letting the user determine what they want to do next. But what I'm referring to when I say other workflows is think of how you would invoke random forests day after day, or in a script. And just like if you're familiar with the caret package in R, it enables you at a slightly higher level to vary parameters, if you will. And I'm thinking of internalizing more of those kinds of things. So that way you only have to sort things once. And if you're in a multiple node framework, that's a big deal. So that's what I was referring to. But yeah, I was not talking about other ways of resampling. No, that's what I meant when I said this is under active specification. So, but it'll be there. All right, thank you.